In this video, we're going to cover the concept of magnetic energy and then summarize magnetostatics. So in defining magnetic energy, it's useful to return to the definition of stored electric energy and how we went about deriving that. So when we were trying to derive the energy stored in a charge distribution, you may recall we considered the following situation. We started with empty space, and then we began with a charge Q1, which we then brought into the empty space from infinity. And that costs us no work because there were no charges in the space originally, and so there was no electric field initially present in that space. So moving charge Q1 into the space didn't cost any work. But then when we brought a charge Q2 in, there was an electric field already established by Q1, so it cost us some amount of work to bring in Q2. Then when we brought in Q3, charges Q1 and Q2 were producing an electric field jointly due to superposition, and so there was some additional work required to bring in Q3 once Q1 and Q2 were already there. And we repeated this process many times, which can be give us the result that we see over here for a discrete charge distribution. Or if we add so many charges that the discrete charge distribution becomes continuous, then we end up with this relation over here. So this is how we calculated stored electric energy in a volume V, or in a discrete charge distribution. So the process for magnetic energy, or determining the total magnetic energy, is quite similar. Can we apply the same process? We can indeed, if we start with the equivalent of elementary particles in a magnetic system. So we don't have magnetic monopoles, but we do have magnetic dipoles. And a magnetic dipole, in its simplest form, is nothing other than just a little current loop. So we could say, here's a current loop, and let's bring that in from infinity. So we can try to move this from infinity, and it costs us no work to bring this loop into an empty space where there wasn't already a magnetic field. So let's bring in that loop, and we can draw a little current, let's say I1 flowing on this loop. And there's some corresponding magnetic dipole that's associated with this loop here. Then we will bring in another loop, I2, also from infinity. And this time it costs us work to bring that loop into the space where loop 1 already exists, because loop 1 is producing a magnetic field, and we have a current flowing in loop 2. So there's a force between these two conductors, and so there's work involved in moving this current I2 into whatever position we have chosen for it, and I2 has its own magnetic moment associated with it. And we could repeat this process for many other magnetic dipoles and arrive at a system where we have a discrete number of magnetic dipoles, or add so many magnetic dipoles and pack them so close together that we end up with a continuous current distribution. So the question is, how can we compute the total work done? This is actually a fairly involved process, and what we'll propose instead is to observe the fact that the electric and magnetic quantities are sort of duals of each other. So we know, for example, that the electric field in electrostatics behaves a lot like, is analogous to, I should say, the magnetic field in magnetostatics. And the electric flux density field is analogous to the magnetic flux density field in magnetostatics. And we have these results from electrostatics from before. So these are for a continuous volume charge distribution. And so we can find the total electric energy stored in that volume by computing this volume integral of 1/2 d dot E. And that gives us a result in joules. So that's the total electric energy stored. If we look at the integrand and include the factor of 1/2, if we don't integrate over volume, then we must have started with a quantity that was work per unit volume. So that is an energy density, and that energy density is represented by this quantity here. And notice that its units are joules per meter cubed. Now, if we are in a so-called simple media, so if we are in a simple medium, so by simple I mean that the medium is homogeneous, like it's not changing its dielectric constant and it's isotropic, then we can say that we have, of course, this constitutive relation, this simple constitutive relation between D and E, and this product, or this dot product of D dot E, is going to be equal to epsilon times E dot E. And so this is the same thing as epsilon times the length of E squared. So we have another expression for stored electric energy where we could just take the volume integral of epsilon times length of E squared dV. So applying this duality principle between the E and H field and the D and B field, we can write corresponding expressions for the magnetic stored energy in a volume V and the corresponding magnetic energy density just by replacing D with B and E with H. And these are in fact the correct expressions for those quantities. And again, if we are in a simple medium, there's a very simple constitutive relation describing the relationship between B and H. And we can then write that this product or dot product of B dot H is simply mu times the length of the H vector squared, and write corresponding expressions for the stored magnetic energy and the stored magnetic energy density. All right, so to drive this point home, let's consider a simple example of a magnetic device, well, electromagnetic device that we have analyzed a few times before, but we'll focus on the magnetic energy for this particular case inside a coaxial cable. So to analyze the situation, we need to first write out expressions for B and H. So from Ampere's law, we have derived the magnetic field inside the coaxial cable many times. This is simply equal to I over 2 pi r phi hat. And this is assuming that the current flows, let's say, in the Z direction, and that we have some return current on the shield so that this magnetic field is only non-zero between the two conductors. And it's zero outside, and we could use Ampere's law to find the magnetic field inside the inner conductor. But our focus here is to try to find the magnetic energy stored in this region between A and B, or the inner and the outer conductor. Now, if the space between the inner conductor and the outer conductor has a magnetic permeability mu, then we know that B is just mu times H. So mu I over 2 pi r phi hat over the same region. So if we were calculating the energy density, magnetic energy density associated with this, then it's just going to be mu I squared over 2 pi squared times r squared. So we notice that the energy density rolls off with the square of the radial distance in this case. And if we want to integrate this quantity, this energy density, because this is in joules per meter cubed, so if we want to turn it into a quantity that's just in joules, we need to do a volume integral. So let's write out a volume integral here. And our integrand is the energy density, which we just wrote up above. And then we need to introduce our differential volume element in cylindrical coordinates. So that is r dr d phi dz. So the inner integral over r is between the inner and the outer conductors, which reside at r equals a and r equals b. The middle integral is over phi. This is done between 0 and 2 pi. And the last integral is over z, the length of this cable. So perhaps we should indicate, as we have before, the length of our coaxial cable here. Let's say that it's L, and let's say that this face is z equals 0. So then we begin at z equals 0 and integrate to over length. So this is a fairly easy integral to evaluate because there is no dependence on z or phi. So the phi dependence simply turns into 2 pi, the z dependence simply integrates to L, and then we have a bunch of constants, mu I squared over 2 times 2 pi squared in the denominator, and the integral over r is just dr over r, which is the logarithmic function, natural log function. So our stored magnetic energy is mu L I squared over 2 times 2 pi times ln b over a. Notice that we've canceled off this 2 pi here just to leave with a single 2 pi in the denominator. So this is the magnetic energy stored in the dielectric space between the inner and the outer conductor. And what I want you to pay attention to is that we actually recognize something in the term here. If we look at this mu L over 2 pi term and this log b over a term, this was actually the inductance of our coaxial cable, which we did in a previous example. So if we look at the resulting expression for Wm, we have a factor of 1/2. We have now this inductance, and then we're left with I squared. And you should recognize this as the energy stored in an inductor from circuits, 1/2 Li squared, much in the same way that the electric energy stored in the capacitor is 1/2 CV squared. So once again, we see that there's a corresponding interpretation at a circuit level of these stored energies. So to summarize magnetostatics, we have basically the lower half of this table. We have our fundamental laws of magnetostatics. So the first law here is that the B field and correspondingly the H field cannot have a divergence. This is also the same thing as saying that there are no such things as magnetic monopoles because they would produce a divergent B field. The integral form of this is that over a closed surface S, B dot ds must be equal to 0. So again, we cannot have any net flux leaving a closed surface. This should say integral form. Ampere's law, we've seen before, an integral form, contour integral of h dot dl is equal to I. And we've also seen that there's a corresponding differential interpretation of that equation, that the curl of h is equal to the current density at a point. So we can compare these to the electric cases, which are shown up above. We have Gauss's law on the top row and the conservative property of the electrostatic field on the second row. And a reminder that we see sort of opposite behavior. The electrostatic field can have a divergence but can't have a curl. The magnetic field can't have a divergence but can have a curl. Another important thing to observe here is that the top two equations, which ostensibly describe what we'll call electricity here, or electrical behavior, are completely decoupled from the bottom two, which basically describes magnetism. So this is important because when we look at static fields, it looks like the electrical behavior or electric field and D field have nothing to do with the magnetic field. And for a long time, actually, people thought that electricity and magnetism were two different things. And these equations, in their current form, suggest that electricity and magnetism are completely decoupled from each other. And in fact, it wasn't until Michael Faraday came along and asked the following question. From everything that we've done in magnetostatics, we have seen so far that if we have a current, which is an electric current, it can produce a magnetic field. and we can predict that magnetic field from Ampere's law or Biot-Savart law or using potentials. We've seen this multiple times. So Faraday wondered, is the reverse possible? Can a magnetic field produce a current? And you can see a setup on the right-hand panel here of Faraday's famous induction experiment from 1831, where he was able to create a magnetic field using an electromagnet, which is this battery connected to a coil, and then drop it into another coil, which is connected to a galvanometer here. And he noticed that you can induce a current in that circuit, which is labeled B here. So the magnetic field produced by that electromagnet was able to produce a current in this circuit. And that leads us to the last unit in EC 221, which is on electrodynamics, when we have time varying electric and magnetic fields and what happens in interesting circuits such as this.